Hello everyone and welcome to my channel. My name is RF and today I'm going to talk about two important theorems in circuit analysis known as Thevenin and Norton theorems, as you can see here. So these theorems were originally stated in DC circuits only. However, we can extend them to AC circuits. If you want to use them in AC circuits, we need to use phasors that we will discuss it later in another show. For sure, I'm going to just get into that later. For now, let's just focus on DC circuits. So in terms of DC circuits, Thevenin theorem states that any linear electrical network that contains only voltage sources, current sources, and any combination of resistors, as you can see here, voltage sources, current sources, and resistors, can be replaced by a voltage source in series with a resistance. We know that voltage source as Thevenin voltage and that resistance as Thevenin resistor. So let's see that in an example. Any combination of resistors and sources can be simplified down to a single voltage source over here in series with a single resistor that we know it as Thevenin resistor. So I want to see my circuit from this port, which I'll call it port AB. So I only want to see my circuit from this port AB. So I can just remove all these elements and replace them with only two elements, Thevenin voltage and Thevenin resistor. Now let's see how to calculate these two elements from a main circuit. So Thevenin voltage, in order to calculate Thevenin voltage, what we do is that we open the selected port. As I said, I'm going to see my circuit from this port A, B. And this eye is actually my eye. I'm just looking at my circuit from this point of view only. So I open the circuit and then calculate the voltage across this port. So it's shown here, it's the same as A, B, the same port. So I just opened from here and I removed my load, which was 2 kilo ohms, and then I tried to calculate the voltage across AB, and that voltage would be my Thevenin voltage. So I will solve this problem as an example. Let's now see how to calculate Thevenin resistor. So in order to calculate Thevenin resistor, we open the selected port, again the same as Thevenin voltage. So we open it, but this time we turn off all independent voltage and current sources. So as you know, if I want to turn off a voltage source, it would be changed into a short circuit, just a piece of wire. And if I am to open a current source, I just change it to an open circuit, as you can see here. So for voltage sources, just replace them with short circuit, and for current sources, replace them with open circuit. And your circuit now turns into this. In this circuit, all you need to do is to calculate the equivalent resistor now, which is the resistor seen from port A, B. So I'm just watching my circuit from this port only. So now calculate the equivalent resistor in this circuit, and that resistor is your Thevenin resistor. Now let's solve this problem to figure it out better. Let's try to solve this together. So in order to solve this problem, I'm going to use superposition theorem. I hope you guys remember from previous courses for superposition. I want to just calculate the voltage across port A here and B. So in order to solve this voltage, I'm going to use superposition theorem, meaning that I want to see the effect of 5 volt once while the 2 milliamp is off, And another time I want to see the effect of 2 milliamp current source while the 5 volt voltage source is off. So yeah, let's do it together now. Okay, let's just try to just break this circuit into smaller pieces. It's gonna go with 5 volt in series with 1K, another 1K here, and I have 0.5K. And here, this current source is open because I only want to see the effect of my 5 volt voltage source. Okay? And then this one is 1K, this one is 0.5K, and this one is again 1K. What I need is the voltage across this port, also known as port A, B. Okay, now let's calculate it. I have a 5 volt source here, and if here is open, is there any current passing here? The answer is no, because the circuit is open, so no current. This voltage is the same as voltage here, and this voltage is the same voltage as here, this point. Okay, so port AB is transferred from here all the way to here. A very simple voltage division rule tells me that I have two equal resistors and there's a 5 volt source, so the voltage has to equally be divided between these two. Easy. So the voltage of AB would be 5 divided by 2, or 2.5 volt. So that's actually my Thevenin voltage. Easy peasy. Sorry, no, this is not Thevenin voltage. I call it voltage Thevenin 1. So I have like two effects that needs to be added together. Now let's try to solve this circuit, but this time I turn off this source, 1K, 1K, and over here I have 0.5K, and now I'm gonna turn on my current source. Just forgot my current source. Let's have a look very quickly. It was 2 milliamp. Okay, so my current source is 2 milliamp, and again here is port AB, A and B. Okay, so it's easy. I have 1K, 1K, and the heads and tails of these two resistors are connected together. I can simplify this. 2 1K resistor would be 0.5K, the equivalent resistor from here. And then this 0.5K is in series with this 0.5K. And then I have 2 milliamp current source that goes into both of them. So you know when two resistors are in series, the currents are the same. And this is the voltage that I'm trying to figure out. So the equivalent resistors, when two resistors are in series, the equivalent resistor is just the addition of the two of them. So 0.5K plus 0.5K would be 1K. So I try to just simplify the circuit. Again, 2 milliamp. So it's easy. Now the voltage of AB is 2 milliamp times 1K. So milli and kilo just cancel out. I will have 2 volt. So let's now see the Thevenin voltage. I have 2.5 volt with Thevenin 1, and with Thevenin 2 is 2 volt. So 2 plus 2.5, I just come to conclusion that my with Thevenin is actually with Thevenin 1 plus Thevenin 2 through superposition theorem, that would be 4.5 volts. Okay, now let's try to calculate equivalent resistor from this circuit. So the equivalent resistor, as we mentioned, we just turn off our power sources. Here I have a voltage source. If I want to turn off a voltage source, it will be replaced by a short circuit. Here I have 1K, 1K. This one is 0.5K, 1K, 1K. And the current source is just an open circuit. And I try to find equivalent resistor from here. Again, this is just my eye. I'm watching the circuit from this point onward. Okay, so the equivalent resistor 1K and 1K are in parallel. So that becomes, when two resistors are in parallel, so the equivalent resistor is less than each one of them, 0.5K, and that becomes in series with this 0.5K, and there you go. Here is the equivalent resistor. My equivalent resistor is 0.5 plus 0.5 is 1 kilo ohm. This resistor is also known as Thevenin resistor. That's the same as my Thevenin resistor. So I have 4.5 volt, that's my Thevenin voltage, in series with 1K resistor, 1K. And if you guys remember, we had a 2 kilo ohm load. I can just put it back now. This is exactly the same port AB, if you remember. Port AB. I'm watching the circuit from this port and I see one 4.5 volt voltage source in series with 1 kilo ohm resistor, which is in case now in series with another 2 kilo ohm load. Can you calculate the load current now? It's easy, yes. 4.5 divided by 3K, whatever is the answer. I can calculate all other items. Easy job. I can calculate my load voltage now. I can calculate any necessary item once I figure out my Thevenin equivalent. So very quickly, I want to mention Norton's theorem. So once we calculate Thevenin's theorem, Norton theorem can easily be calculated from my Thevenin theorem. So let me just draw it again here. If this is my Thevenin theorem, and over here I had my load. So if this is my Thevenin theorem, that's V Thevenin. This one is R Thevenin. This circuit is equal to, this one is I Norton in parallel with R Norton. And again, I'm going to just point out this one is the same port. Same port. Port A and port B, okay? This is the same port A and port B. So just consider the same point, but this time instead of having a voltage source in series with a resistor, I have a current source in parallel with the resistor. Okay, how do we calculate one from another? Just easy. R Thevenin is exactly the same as R Norton. So R Norton is exactly the same as R Thevenin, which is 1 kilo ohm. How can I calculate I Norton? Just simply use Ohm's law. I equals V over R, right? So I Norton is V Thevenin divided by R Thevenin. So 4.k divided by 1, which is 4.5. That was volt. This one is K, so 4.5 milliamp. Perfect. So this is 4.5 milliamp. So this is my Norton equivalent taken from my Thevenin equivalent. We could have just directly calculate Norton circuit, and then from our Norton circuit we could have calculated our Thevenin circuit. So these two are interchangeable. So you can easily just change them from Norton to Theorem to Thevenin. So the Norton and Thevenin theorem are equal actually. Thank you very much, and I try to solve more problems in next sessions to make sure that we understood every part perfectly. Thank you very much, and if you liked the contents that I provided today, please do like this video and subscribe to my channel, and please share it so that we help everyone grow together. Thank you very much.